Hey, we have one more example for chapter 4. This one I'm putting in here because it combines several of the topics that we talked about. So I thought this one would be a good one. Plus, when students see a picture like this, they tend to automatically assume it's going to be an impossible problem that they won't like. So it's a good one to do for an example. Let's go ahead and read through it. We're going to have separate streams of air and water flow. Now let's look. So here is air. Notice it's going through this compressor. Down here we've got this water flowing through a heat exchanger. Alright, so those are the two separate flows. And we'll talk more about it when we get done reading the problem. Alright, so we've got air and water flow that's going through the compressor and the heat exchanger arrangement. We're going to have steady state operating data that is provided on that picture. Heat transfer with the surroundings can be neglected, so that's good. And all of the kinetic and potential energy effects can be neglected, so that's good too. Air is going to be modeled as an ideal gas, which we like that because that's a nice way of giving us some equations. Now we're going to determine the power required by both compressors in kilowatts, and we want to find the mass flow rate of the water in kilograms per second. Okay. Now let's look and see what's going on here. And I know these numbers are kind of blurry in this video. I can't really zoom in anymore, otherwise it just looks worse. So bear with me here. We're going to have air coming in this compressor. All right. Notice the compressor has got this W dot term on here. We'll talk about that when we get to the equations. And then the air is going to leave the compressor A. It's now got a pressure of 3 bar and a temperature of 600 kelvins. Notice up here it started with a pressure of 1 bar and a temperature of 300 kelvins. We also had mass flow rate given. Okay, so pressure went up, temperature went up as it went through this compressor. Then it's going to flow through this heat exchanger in these top coils, and then it's going to come out the other side and it's going to enter compressor B. Now at this point, notice we had a reduction in the temperature. It started out at 600, now it's at 450. Pressure did not change though. Then it enters into compressor B. We've got a W dot term here, and then it leaves compressor B. It now has a pressure of 9 bar, so pressure went up, and temperature also went up to 800 kelvins. Now at the same time, we've got this water flowing through here. This is cooling water. The water is going to enter at a temperature of 20. Pressure is 1 bar. Flows through here. We're going to have transfer of heat, and then it exits. Temperature has gone up. Alright, so it's gone up to 30, and then pressure stays unchanged. So P5 equals P6. Okay, so quite a few things going on there. That's why this is a good, interesting problem to look at. Now, what we want is we want to find the total power required by both compressors. So that's these little W dots right here. That's what we're looking for. So we want WCVA dot and WCVA or WCVB dot. That's what we're looking for. Because remember, compressors have to have that external power in order to make them run. So we want to find out how much we need supplied to each compressor in order to get this process done. Alright, so let's start with A. And we'll work on finding these two things. Now let's go ahead and we're going to analyze compressor A first. Compressor A. Let's write down an energy balance equation for this. We'll have 0 equals Q dot minus W dot plus M dot times H1 minus H2. Okay, so now that we've got our equation, let's go ahead and look at this. Q dot, are we going to have this term? Nope, goes away. And why does it go away? Because it said our heat transfer can be neglected. And you know what, I just realized we did not highlight our keywords. So let's go ahead and do that. The main keyword we're going to have here is ideal gas. And we've got steady state. All right, now that we did that, let's go back to this. Let's go ahead and solve for W dot because that's what we're wanting. So W dot for control volume A is going to equal M dot times H1 minus H2. So now we have that. We need H1 and H2. Now notice this is an ideal gas, so we will use the ideal gas table, which is table A22. Looking in our table, if we look at the temperature for 300, here is the value we have. So H is going to be 300.19. Again, remember this is the ideal gas table for air. All right, so we got 300.19. That'll be H1. And then for H2, we have a different temperature. We're at 600 now, so our temperature went up, which means our enthalpy is going to be 607.02. Let's write that one down. And the units for both of these are kilojoules per kilogram. And again, these come from the ideal gas table, which is A22. All right, perfect. We're getting close. Now, notice M dot, that was given to you. It was 0.6. We have that. We have both H numbers. We can solve now for W dot, for control volume A. We have 0.6 kilograms per second times 300.19 kilojoules per kilogram minus 607.02 kilojoules per kilogram. Notice kilograms goes away. We are then left with W dot for control volume A equal to negative 184.098 kilojoules per second. So, all right, that's part one that we needed. All right, so we need to find two W dot terms. So this is the first one that we needed. So W dot for, now notice on this control volume A here that we have a negative sign. Remember, the negative sign always means we're going to have energy transferred from work coming into the system. All right, so that negative means you have to have that external power supply. Now we're going to do the same thing for compressor B. Let's do that over here. For compressor B, now we have to figure out our mass flow rate. Now remember, this is all air coming through here. All right, so the air flows through compressor A, goes through this heat exchanger, goes back through compressor B. All right, so our mass flows then, since we are steady state, we're going to have M1 dot equals M2 dot equals M3 dot equals M4 dot. So they're all the same. Nothing's changing that mass flow rate. Now we want to find the power required by compressor B. So that's this W dot term. That's going to be our external power that's being supplied. Now if we look at our equation for compressor B, we're going to have something similar to this. We'll just have the subscripts for compressor B. So if we look over here, we'll have WCVB dot equals M3 dot times H3 minus H4. Again, we have an ideal gas, so you're going to look in the ideal gas table and pull out values for H3 and H4. We have temperatures at both of those locations given. This again will come from table A22. H3, if you look up the temperature 450, Our H is 451.8. Let's write that one down. That's kilojoules per kilogram. And then H4, when the air leaves, it has heated up to 800 Kelvin. We go to 800 Kelvin. H is going to be 821.95. And we get kilojoules per kilogram. Now we got our values. Let's go ahead and plug them into this equation here. The total power required by compressor B is going to be 0.6 kilograms per second times 451.8 minus 821.95 kilojoules per kilogram. Notice kilograms go away. And this is going to give us negative 222.09 kilojoules per second. And that is total power required by compressor B. Again, notice the negative sign. The negative sign always indicates external power coming in. Right? We've got the energy transfer from work coming to the system. So let's just write a note here. So that negative sign means we have a power input. All right. So pretty awesome so far, right? We already found 2 of them. Now we just need to find the mass flow rate of the water. Let's look at that part. We're almost done. So on B, we want to find MW dot. That's what we are looking for. All right. Now here we got steady state again. So M5 dot has to equal M6 dot. Like that. Now we're going to write our equation. Now our control volume, what we need to do is we need to look at everything inside of this exchanger. Now for the compressors, we literally just looked at the compressors. All right, so our control volume would have just been that and then that. All right, we were just looking at those. Now for this heat exchanger, we want to find the mass flow rate of water, so I'm going to look at this thing here. So everything inside of the heat exchanger. And let's make a note about that. So CV is everything inside of the heat exchanger. Okay. And let's write our equation out. We're going to have 0 equals Q dot minus W dot plus the sum of the inputs. We're going to have mass flow of the inputs times H for all the inputs minus the sum over all of the outputs of M dot for the outputs times H for the outputs. Now, we had to use this one for multiple inlets, multiple outlets because we have basically 2 inlets right here at 5 and then at 2, and we have 2 outlets. We have one at 3, one at 6. Okay, now that we have that, let's go ahead and see if we can simplify this at all. Do we have this Q dot term? No, because it's telling us to ignore heat transfer with the surroundings. So this goes away. Do we have a power supply needed for the heat exchanger? Nope, don't need that, so that goes away. We're left then with just these 2 pieces here. Let me switch pages so I have some more room. And here it is. Okay, now that we've got that set up, let's go ahead and rewrite this equation using our terms from our specific problem. We're going to have 0 equals, let's look at the input for 2. So that's the one coming out of compressor A. That's going to give us M2 dot times H2 minus H3. And we're going to have this because remember, we have steady state. So M1 dot equals M2 dot equals M3 dot equals M4 dot. Next, we're going to have plus M5 dot times H5 minus H6. And same thing here. Remember, down here for the heat exchanger, M5 dot is going to equal M6 dot. So let's just use one of those. Okay, so we'll just use M5 dot and then put the difference with the enthalpy. All right. If it's easier for you to see it, you could write the whole thing out. I'll put it over here on the side. So it'd be 0 equals M2 dot times H2 plus M5 dot times H5 minus M3 dot times H3 minus M6 dot times H6. But then we know that M2 dot equals M3 dot, M5 dot equals M6 dot. So I just simplified it and wrote it in this form. Now that we have that, let's go ahead and see what we need next. Now we already found H2 and H3. We don't have H5 and H6 yet. We need to find those. Let's look at those. Now for H5, we've got water, temperature is 20 degrees Celsius, and we've got a pressure of 1 bar. If we look at our table for the water at a pressure of 1 bar at that entrance 0.5, our saturated temperature here is 99.63. Our temperature is at 20 degrees Celsius. So that means we have a compressed liquid at that point. Now remember, we can make an assumption that that is approximately equal to the value from the liquid vapor table. And if you remember from that section when we were doing approximations, we wrote down that our enthalpy could approximate or be approximated with HF at your given temperature plus VF at your given temperature times the pressure minus the saturation pressure. So we're going to use this equation to do our approximation. And you might be wondering why we need to do this approximation. You might be thinking, well, why don't we just go to the compressed liquid table and pull the data out and use that, because that would be easier. Well, if you look at the compressed liquid table, notice your lowest pressure here is 25 bar. We're at a pressure of 1 bar. So we have no way of pulling that data out of this table. All right, so that's why we're going to use this approximation. Okay, so I'm not just randomly deciding to use this. It's because the data is not in the table. So anytime you can't find your specific values in the table for compressed liquids, you always have the choice to do this approximation. Now HF at our temperature, which is 20 degrees Celsius, is going to be 83.96. That's kilojoules per kilogram. And I'm going to go ahead and convert that to Newton meters. Let's do 10 to the 3 Newton meters per kilogram. We'll do that conversion. And then we need VF at our given temperature of 20 degrees. So if you look it up in the saturated water table, you will get a VF number of 1.0018. That's one of those where you need to divide by 1,000. Units will be cubic meters per kilogram. Now we're going to not divide, we're going to multiply by the difference in these pressures. Our pressure is 1 bar. Saturation pressure is 0.02339 bar. And again, let's go ahead and get in Newton meters. So our conversion will be 10 to the 5th Newton per square meter per 1 bar. And that's the end there. Now what you're going to end up with, you'll end up with units of kilojoules per kilogram. when you do all of this. So H5, this is for H5 by the way. H5 then is going to be 84.05 kilojoules per kilogram. Right, so now we have that. And then H6, you're going to do the same thing. So you would just use the same equation. You're just going to look up your values at a temperature of 30 degrees. Let's put approximately here. So H6 will approximately be 125.89 kilojoules per kilogram. And let's just write a note. So same step as finding H5. But we're going to use T equals 30 degrees Celsius. Now that we have that, we have our enthalpy numbers, we can go ahead and solve. All right. So if you plug them into this equation here, you can go ahead and solve for M5 dot. Let's call this equation 1. We haven't used that yet. So go to that equation 1, plug in your values. We know M2 dot, we know H2, we know H3. We're looking for M5 dot. We know H5 and H6. So just plug in your numbers and then solve for H5. I'm out of room here, so I'm not going to write all that down, but that's how you do it. So M5 dot is going to be 2.226 kilograms per second. Okay, and that's your mass flow rate of the water in kilograms per second. Hopefully you like that problem. I think it's a good one. Like I said, students always see those problems that look kind of complicated and they think they're impossible to do, but they're not really impossible. You just have to break it down into all of the little pieces. Okay, that's the end of chapter 4. 2 more chapters to go. I'll see y'all for the next one.